Hi everyone, I'm Youjie, a PhD student from UIUC. In this talk, we propose a new ML framework called Harmony and use it for training massive models on commodity servers. This work belongs to Microsoft Research and was in collaboration with Amar, Derek, Jakub, and Amson. Over the years, the DM model sizes are growing exponentially, and they continue to solve more complex problems. 10 years ago, a small AlexNet can only classify simple images. Now, a GPT-3 with almost 200 billion parameters can write a realistic paper of the nature. Just last year, DM model size have reached 10 trillion. As a model size grows, they become harder to train, especially they consume huge amount of memory. Training the GPT-2 of 1.5 billion parameters already requires 128 GB memory. This is because when we break down the memory requirement, we can find that parameters are only a tiny fraction of the total memory usage. Now, training massive models demands so many resources such that only the elite, the big companies who own the data center of GPUs, can be still in the game, like using 1,000 GPUs to train a GPT-3. But most researchers, the mass, might have only limited resource, like a single server with several GPUs. Do you and I, who have only such a server, even stand a chance of developing, debugging, and training massive models? In this work, we explore how to train massive models on commodity servers, especially how to train efficiently. One of the major challenges is a memory footprint far exceeds the memory capacity of a GPU. Training GPT-2 requires order of magnitude more memory than the capacity of a V100 GPU. The promising solution is a GPU memory virtualization, which uses a large CPU to back the small GPU, and swap data between CPU and GPU memory. Prior works have already shown this technique allows a single GPU to train larger models. But it comes with a price of excessive swapping overhead. For example, a model is going to compute several data batches in a timeline, and the GPU memory is virtualized, can hold one layer at a time. At the first data batch, the GPU needs to swap in the necessary model state to compute, then swap out for saving state changes. When the second data batch comes, the GPU needs to do this swap in, swap out again. These repeated swaps give excessive overhead. Even worse is that we can have a swap bottleneck. In practice, training large models is never done with a single GPU, but with multiple GPU for parallel training. And all GPU can swap concurrently and swap to nowhere but to the CPU through a PCI tree. Then the root PCI link can easily become the bottleneck, because it is often oversubscribed by 4 to 8 GPUs. Another promising solution is model pipeline parallel training. They partition a large model into smaller parts, such that each part requires less memory can potentially fit into each GPU. This is great for models that can fit collective memory capacity of GPUs. But sadly, on commodity servers, even with all GPU combined, their collective memory capacity still cannot meet the memory footprint. This is because either the model size or data size is too large, or the GPU is low end, or we don't have enough GPUs, which are common in commodity servers. It is time to think, how about combining pipeline training with memory virtualization? Unfortunately, it's still inefficient. So far, we have suffered from swap overhead, swap bottleneck, and even unbalanced swap in pipeline training. We find these swap inefficiencies are hard to solve because they are caused by the fundamental limitations in today's ML frameworks. First, the scheduling is too coarse-grained. As shown earlier, PyTorch schedules the entire model to compute the first data batch before the second. Second, the binding to devices is too early. For example, even in the user script, we have already fixed the first part of the model to first GPU and the second part to second GPU. As a result, we have poor flexibility and resource utilization, making the swap inefficient. To overcome these limitations, we propose a new ML framework called Harmony for efficiently training massive models on commodity servers. The key ideas are three. First, we decompose the coarse-grained model data into small pieces. Then we combine these pieces into fine-grained tasks. Third, we late-bind task compute swap onto devices and links. This can bring us three benefits. First, we boost the performance by maxing the swap efficiency. Second, we provide single GPU abstraction for multiple GPU training. Third, we provide the flexibility to reconfigure different modes of parallel training. For the performance goal, we introduce 4 key optimizations. First, input batch grouping. In vanilla training, each task needs to swap in its state like weight to compute multiple input batches that are scattered in the timeline. This suffers from repeated swap. With input batch grouping, we let each weight to run across a group of input batches before swapping out, such that we reduce repeated swap into a single swap. Second is just-in-time scheduling. In vanilla training, a task might not be executed, even if its required input are in memory. For example, an update task is not executed immediately, even if its weights are already available after its backward task. This causes unnecessary swap. With JIT scheduling, we execute a task as soon as all its inputs are available in memory, before they get swapped out. This avoids unnecessary swaps. Third is generalized peer-to-peer swap. In vanilla training, each GPU memory is virtualized individually without knowing other GPUs. As a result, all tensors are swapped to the CPU and cause a swap bottleneck. With P2P swap, we move the original CPU-GPU swap onto P2P link such that no more CPU-GPU swap. To put it together, let's look at this simple example. First, suppose we have all tasks decomposed already. There are 3 types of tasks, forward, backward, update. And each task contains layer and micro batch. Then Harmony will perform these optimizations. The scheduled result can then be unrolled in timeline like this. As can be seen, on the GPU1, the first 2 tasks are grouped together, such that they reuse the layer 1 state in memory by computing across 2 micro batches. So on and so forth to group all forward and backward tasks. Then the output of layers are always P2P swap to next layer instead of swapping to CPU. Also, the update task happen just in time, without waiting their layer state being swapped out. So this task forms a virtualized pipeline called wraparound pipeline, running across 2 GPUs without capacity constraint. Lastly, compute swap are running under the hood, which are handled by Harmony runtime. Our last optimization is layer packing. It is very challenging because not all layers are created equally. Naively packing different layers together will give you unbalanced load across GPUs. Also, different micro batch sizes give different level of imbalance. Even worse is that we have drastically different layer truth between forward and backward. Fortunately, with Harmony's layer packing, we balance the load of layer packs across GPU for each micro batch size. Even better, we pack differently for forward and backward. Especially, we search a 4-dimensional design space of forward and backward to find the best configuration for fastest training. We implement Harmony with pure Python code on top of PyTorch. We evaluate Harmony on commodity servers or with 4 gaming GPUs. Note that our collective GPU memory capacity is far less than memory footprint of massive models. We compare with 4 highly optimized baselines. First is a data pattern enhanced with GPU per GPU memory swap. Second is gpipe. Third is the most recent pipe dream to BW. This memory swap uses recent IBM's large model support library dedicated for fast tensor swaps. Last, the state-of-the-art zero infinity and enhanced version of data parallelism plus swap. Now, let's look at how Harmony benefit training. We compare the throughput of all approaches at different mini-batch sizes. At the mini-batch size 16, we can see that from the baseline DP swap, Harmony swapped the training by 7.6x. Even from the SOTA zero infinity, Harmony still speed up by 2.2x. Importantly, when we scale up the mini-batch size, the Harmony becomes faster and faster. This is a result for training GPT-2. Other massive models shows a similar result. To understand the speed up, we compare the swap load for all approaches and plot their global swap volume in terabyte on a single mini-batch. At the mini-batch size 16, the baseline DP swap only 0.7 terabyte of tensors, but Harmony swap less, only 7 gigabyte, reducing swap load by 100x. When we scale up the mini-batch size, the Harmony magnifies this reduction until 9.3 terabyte of swap becomes only 30 gigabyte. Harmony reduced swap load by 2 orders of magnitude to achieve this significant speedup. Lastly, we check the correctness of training in Harmony. We compare the training curve of Harmony of 4 GPU to the baseline with a single GPU for fine-tuning GPT-2. Harmony achieves exact match for training loss for every single training iteration. This validates not only the correctness of Harmony, but also our promised single GPU abstraction plus synchronized SGD convergence. To sum up, training massive models requires huge amount of memory. Naively virtualizing GPU memory has excessive swapping overhead. We propose Harmony for efficiently training massive models on commodity servers. Harmony speed up training by 7.6x, reduce swap load by 300x, provide synchronized HGD semantics, and scales linearly. Harmony is now open source. We advocate rethinking how ML frameworks should schedule, compute, and move data for training massive models on commodity servers for the mass. Let's train massive models in Harmony. Thank you.